In our introductory module, we considered the case of trying to predict the failure of O-rings in shuttle launches, and we saw that the methods that you have covered previously in regression 1 and regression 2 are not adequate for addressing this question. In this module, we will revisit the example, look again at the motivating Challenger disaster which led to this question, and formulate tools which we need to address this situation. We will, to begin with, apply the methods which we learnt in regression 1 and see that they do not lead to a satisfactory answer. We will look at the theoretical drawbacks if we continue to apply the methods of regression 1 to the case where we have a percentage as an outcome. Briefly, we will look at an overview of the tools, fitting procedures, and ultimately we will answer the question, which is, could we have predicted the Challenger disaster? In our introductory module, we had looked at the failure of O-rings and whether we could have predicted the Challenger disaster as a motivating example. In this module, we will look further at methods for predicting the failure of O-rings and see what they say about our ability to predict the Challenger disaster. So to recap again, let us look at the slides we saw in the introductory module. So this is a video which looks at what happened to the Challenger space shuttle. That was a video of the Challenger space shuttle going off course and exploding over the Atlantic Ocean. We also saw this slide, which is a result of a naive application of linear model theory to a dataset on O-rings, which is available in the Faraway library in R, and we saw that the results are a little disturbing in the sense that they lead to predictions which ultimately must lie outside of 0 and 1. We saw also that this could be fixed by introducing the concept of a link function, and that there are many choices of the link function, two of which have been listed here, the logit and the Probit link. The logit and the Probit link are the common choices of the link function for the case when we are trying to model proportions or percentages. We saw also the result of using the logit and Probit links for this data, and we see a more satisfactory answer, as also the fact that the predictions from both models are quite high. Let us now step back and look at this example in greater detail. So first, the Challenger disaster. The Challenger disaster occurred in January of 1986 when the space shuttle Challenger exploded a few seconds into its launch. Now it turns out that there had been controversy about a piece of equipment called the O-ring seals and their performances at lower temperatures. The O-rings are a piece of equipment, and there are 3 O-rings in each of the 2 boosters of a satellite, leading to a total of 6 O-rings. The question was, could the failure of the O-rings have been predicted? Such a question arose because it turns out that the O-rings were not necessarily tested under all experimental conditions, and in particular there was some concern that the performance of the O-rings was suspect at lower temperatures. The O-rings had been tested at temperatures around 40 degrees Fahrenheit and above in experimental conditions, but at the time of launch the temperature was 31 degrees Fahrenheit, and so there was some suspicion even before the launch that the O-rings could fail. There was a massive controversy about this following the Challenger disaster. Now let us explore this further looking at a dataset which is called the O-rings dataset. It is available from the Faraway library in R. So here is a description of the O-rings dataset. Now, as I just said, the 1986 crash of the space shuttle Challenger was linked to the failure of the O-rings. To be able to address this problem, the O-rings dataset in R looks at data on 23 previous shuttle missions. The O-rings is a data frame with 23 observations on two variables. The first is temperature, which is the temperature at the time of launch measured in degrees Fahrenheit. And the second variable is damage, which is the number of damage incidents out of 6 possible. That is, it is the number of damaged O-rings out of the total 6. This dataset has been discussed in detail in a JASA paper by Dalal, Fowles and Hoadley called The Risk Analysis of the Space Shuttle. It has also been explored more in the Faraway library and the associated companion by Julian Faraway. So here is a glimpse of the dataset. In the first column we are looking at temperature measured in degrees Fahrenheit, and in the second column we are looking at the number of damaged O-rings where the total is 6. Now we can see some suspicion from this dataset that at lower temperatures there is indeed a greater chance for the O-rings to fail. We can see one outlier, which is a situation when the temperature was 53 degrees Fahrenheit and 5 of the O-rings failed. We can also see that at none of these shuttle launches was the temperature near 31 degrees Fahrenheit, and thus to answer our motivating question of whether failure of O-rings can be predicted at 31 degrees Fahrenheit, we need to find some kind of model which will explain the data. So let us first begin by doing the naive analysis. So to start with, I call the Faraway library and the O-rings data. I plot the data, and then I fit my naive linear model where I'm looking at the proportion of damaged O-rings out of 6, and I regress this on temperature. So this has been done using the LM function in R, which is used to fit the usual linear model, and I have stored it in an object called LMOD. I am also plotting the regression line on the scatter plot using the command abline LMOD. So this is the plot which results from running these commands, and we see as before our usual disturbing result that this line, if extrapolated sufficiently, will lead to predicted probabilities which either are negative if we go above about 76-77 degrees Fahrenheit, or they will lead to predicted probabilities which are above 1 if we extrapolate to sufficiently lower temperatures. So this is not acceptable, and I need to find a means to rectify this. So technically these are the violations of the linear model which occur when we try to apply the linear model to cases when we are predicting proportions or percentages or even counts. The first is that the errors are not normally distributed. Now think of the regression equation y equal to x beta plus e. Now if y is binomial, then obviously the right hand side of this equation cannot be normally distributed, which is the case that would happen if the e's were normally distributed. So this is my first violation. The second, it is well known that the variance of the binomial outcome b n pi is given by n pi into 1 minus pi. In the example in which we are considering, pi is a function of T or temperature, And this means that the pi's are different for each individual. Now, if the pi's are different, then the variances must also be different, and we have a situation where there is heteroscedasticity. So this violates the normal homoscedasticity assumption of the traditional linear model. However, it is not a violation which can be fixed using the usual tools we have learned to deal with heteroscedasticity, because there is something deeper. And this is that while the mean is n pi for a binomial variable, the variance is n pi into 1 minus pi. So not only is there heteroscedasticity, there is something deeper, which is that the variance is a function of the mean. So the moment we specify the mean, we are also automatically specifying the variance, and we cannot model the variance independently. The third is that the predictions lie outside the range. We have seen this in the plot, where if we fit a linear model and we continue to extrapolate this line, at some point the line has to reach beyond 0 or beyond 1. The fourth is the idea of nonlinearity. Now we know that when we say linear model, we do not mean linearity in the covariate, but rather linearity in the parameters. As long as we have linearity in the parameters, all the results from the Gauss-Markov setup will hold, and we can use this to frame our inferences. Here I am considering nonlinearity in the covariate. Now we have seen that fitting the linear model to temperature results in a line, and by the definition of a line, this is not bounded and at some point must go beyond 0 and 1. However, in many cases, it might be possible to argue that once we go to extremes of the exposure range, my outcome will tend to plateau off. And thus, linearity in the covariate, which is assumed by the linear model, the simplest linear model, is not necessarily applicable, and we need to find ways to account for this nonlinearity also in the case when our outcomes are proportions or percentages. What then would be an appropriate way of modeling this data? Well, one, of course, could be to try and find a transformation of proportion and try and reduce this to a linear model. But let us see if a more fundamental approach is possible, starting from the assumption that we have a binomially distributed random variable. So the first line on this slide gives the probability mass function for a binomial variable. This is well known. Probability yi is equal to small yi is ni choose yi pi to the power yi into 1 minus pi to the power n minus yi, where yi takes the value 0, 1 up to n. On the second line of the slide, I have introduced something called the linear predictor, which I will refer to by eta I. So eta I is simply a linear function of the covariates and also of the parameters. Now, just as for a linear model, it is enough for us that eta I is a linear function of the parameters, and we do not really care if the covariates here are linear or in some known transformed function. So again, I have written the PMF of the binomial distribution, and I have written a linear predictor eta I, which is a linear function of the covariates. Now recall that my original intention was to relate pi to eta I. The usual linear model says that pi is equal to eta I, and we see that this is unsatisfactory for various reasons. So let us see if we can fix this. Now, one way of fixing this could be to say that eta I is not equal to pi, but rather that eta I is equal to some function of pi which can take a value anywhere on the real line. To this end, I have introduced three link functions here. The first is called the logit link, and here we say that eta is equal to log of p by 1 minus p. The second is called the Probit link, and here I have said that eta is equal to capital phi inverse p, where capital phi inverse is the inverse CDF of the standard normal distribution. The third is the complementary log-log link, where we say that eta is equal to log of minus log 1 minus p. Each of these functions is called a link function, and of course in any application it is necessary to decide first on which link function we must use. For various reasons, the logit function is considered the most natural and is often the default choice in software for the case where we have binomial outcomes. But there are many situations where a probit or a complementary log-log or even any other function would be more appropriate. Again, this is something which we will explore more in a subsequent module. Now, here I have written the log likelihood function in terms of the predictors. So this is the same log likelihood function which arises from the binomial likelihood, whereas in an earlier slide we had seen this written in terms of the pi's. The moment I am able to relate p to eta, I am able to write the likelihood function in terms of eta. Now recall that eta is a linear function of the covariates and a function of the coefficients beta. So this means that this is the log likelihood function for beta. This leads to some simplifications. The most important is that we no longer need to develop new tools, because the moment I can write the likelihood for beta, I know that I have the well-tested tool of maximum likelihood for purposes of inference. Now it turns out that fitting the maximum likelihood is not as easy as in many standard situations, because the likelihood equations do not have any explicit form. This means that I cannot extract beta from this equation, but it is an implicit equation in beta. However, it is still well behaved, and I can solve this by Newton-Raphson type methods. There is a variant of the Newton-Raphson type method called Fisher scoring, in which the observed information is replaced by the expected information. For actual computation, we can do this in an iterative form using an algorithm called iteratively reweighted least squares. It turns out that the model can be fit by iteratively fitting a sequence of least squares on a newly constructed random variable. More on this later in a subsequent module. However, the take-home message from this is that the minute we are able to calculate our maximum likelihood, we no longer need to develop any extra methods, but we can fall back on maximum likelihood asymptotic theory. So this means that we can exploit the asymptotic normality of the maximum likelihood estimator for finding confidence intervals, and for testing, we have three ready-made tests, which are the Walls test, the score test, and the likelihood ratio test, which can be applied to any situation in which we are able to write down the likelihood, and the likelihood satisfies some standard conditions, which it does in this case. So let me try and fit these new techniques to my O-rings dataset. To do this, I call a function called the GLM, which is very similar to my LM function. Now, as you can see from this piece of code, my outcome here is a matrix with two columns, where the first column is damage and the second is 6 minus damage. So the number of successes and the number of failures. It is regressed on temperature. A new part of this code is that family equal to binomial. And I'm using the dataset O-rings. So I fit this using the GLM command, and I store the result in the object logitmod. When I do summary of logitmod, it gives me some output including the value of the intercept and the temperature. Now these are the betas which were included in the linear predictor. Now in this particular case, I'm not really interested in the betas per se, but I'm interested in the value of the prediction. However, before going to that, let me also fit the Probit model. So here is the syntax which I would use to fit the Probit model. As before, I'm calling the GLM function. As before, my outcome is a matrix with two columns, where the first column is the number of successes and the second is the number of failures. I'm regressing this in temperature. My family is binomial. However, here there is a new piece of code which says that the link is Probit. Now, in my earlier code for the logit model, I did not need to say explicitly that the link was logit. The reason is that for various good reasons, the logit is considered the default choice for the binomial model. Technically, the logit link is the canonical link for the binomial family, and we shall see later what this means, what it means for a link to be canonical and why this is desirable. The rest of the syntax is as before. I'm using the GLM function and I'm storing this in an object called ProbitMod. When I say summary ProbitMod, this is the outcome that it gives me. Again, these are the regression coefficients which are a part of the linear predictor. But in this case, I'm not really interested in the coefficients, but in the predictions. I can get that using the inverse logit and the p-norm on the linear predictor. And the predictions are given on this slide. It turns out that for the logit link, the probability of failure at a temperature of 31 degrees Fahrenheit is 0.993, while for the Probit link, it is 0.989. So even though they're not exactly similar, they are both very high, and our conclusion is thus that based on the O-rings dataset and the previous information we had on O-rings, it was indeed possible to predict that the Challenger space shuttle launch would result in disaster. To summarize, in this module, we used the example of the Challenger disaster as a motivation for introducing the concept of a generalized linear model. Our question of interest was whether we could have predicted the Challenger disaster, and if we look at it from a statistician's viewpoint, the problem was one of predicting a percentage. We have seen that the linear model has shortcomings, and indeed the assumptions of the linear model are not met in this situation. We have briefly introduced the concept of generalizing the linear model to the case where we have a percentage or a proportion as an outcome. We have taken a quick overview of the methods, introduced the logit and the Probit model, and seen that there are perhaps some model choices, additional model choices, which we did not need to consider when we looked at linear models. In this case, it is the form that we choose for the link function. However, in this particular example, the choice of the link function does not have much bearing on the example, and we can see that the predictions from both the logit and the Probit model are similar, and indeed both of them say that yes, we could have predicted the Challenger disaster.